Okay guys, continuing on with Chapter 2, Section 1. One thing I should have said before I finished up that last video is that the overall plan, what we're trying to accomplish right here, is to get an average rate of change to become more like an instantaneous rate of change. We did say that. And to do that, we want this interval right down here of b minus a to shrink down and get smaller and smaller. Now, the important idea that I didn't mention, though, is that as a and b move closer together, you might get another line right here that looks like this. Now, that original red line was a secant because it was defined by 2 points on the curve. The second red line that I just drew is once again a secant. It's still defined by 2 points on the curve. Those two little red dots that I put right here, if I were to connect those, guess what? That is also a secant because once again, that line was created and is defined by 2 points on that curve. But if we could kind of, and I used the phrase squinting your brain a little bit before, get those 2 points, A and B, to actually move so close that they were actually touching, what would happen then, guys, and I think you can kind of see it from that last line, red line that I drew, what happens then is we actually end up with a little green line right here that doesn't really look like it's defined by 2 points on the curve, but rather it looks like it's defined by only 1 point on the curve. And what I'm hoping you guys remember from the last couple of years is that a line defined by 1 and only 1 point on a curve is what we know as a tangent line. Now, your definition, your understanding of a tangent line might be a little bit off. It might be different based on a pre-calculus preconception there than what we're going to be doing in calculus this year. But the point here is, everybody, that if we can allow our average rate of change to become more and more like an instantaneous rate of change, then our secant line becomes more and more like a tangent line. So that's kind of a big idea that I should have mentioned earlier that I had forgotten to. So let's play around with one function here, guys. And again, I think this one is still relatively straightforward, although we're doing some weird things here that we're going to have to talk about. So we're going to try, now this is very important, we are not actually finding instantaneous rates of change in this section. Every problem that we do in 2.1 that uses the phrase instantaneous rate of change is only going to ask us to estimate that instantaneous rate of change. We're not actually finding it yet because we don't have that tool in the arsenal as it exists right now. So what's happened here, guys? I've given you a function. H of x is equal to a 1/3 x cubed minus 2x minus 3. And we're going to try to estimate the instantaneous rate of change of this function at one particular spot, x equals 2, and we're going to do it 3 different ways. Now, I do want to draw a distinction, everybody, between the difference here in the phrasing of this question as opposed to something that we did earlier, which was one like this. In this example, we were asked to find an average rate of change. But notice here, guys, there were 2 x values that were given to you, negative pi over 3 and 11 pi over 3. That is because an average rate of change requires an interval. It starts at A, it ends at B. And if we were going to graph this, what we're really doing is creating a secant line. And that's the kind of thing that happened, wait, I think I passed that already. That's the kind of thing that happened on this function right over here when we went ahead and drew our secant, which has now disappeared, it looks like. But back to this problem that we're working on right now, notice the difference here. You're being asked to estimate an instantaneous rate of change, not over an interval, but at one unique x value here. An average rate of change or a secant line, they both require 2 data points. But an instantaneous rate of change, or in this case a tangent line, really only requires 1. Although, let's be clear, the way we're going to go about estimating this instantaneous rate of change is to basically do an average rate of change, but over a really small interval. We're going to be coming back to this idea right here. That's a little bit cryptic as you read it, but the idea is sound. That average rate of change becomes your instantaneous rate of change as your denominator's width, b minus a, becomes 0, or at least gets closer to 0. So let's talk about how it is that we're going to do this. Now, I'm going to allow the calculator to do a lot of the work here for me, and I have absolutely no problem with you guys doing the exact same things right now. One of the things I'm hoping to teach you guys in here this year is that computers, or in this case your calculator, being a relatively small and simple computer, can be used to do some of these repetitive tasks for us, and I'm going to try to show you guys how it is that we are going to do that. So the first thing we're going to do, let me go ahead and write out what my game plan here is, everybody. We're going to try to do this first, estimating our instantaneous rate of change by using left-hand intervals. And what left-hand intervals mean is that for each time that we're going to make an interval here, x equals 2 is going to be the value that we're going to use on the right half of our interval. So I'm going to try to create a small interval here that changes some things over there on the left-hand side. So my first left-hand interval, I'm just picking values right here, guys. I want to guess at something that's relatively, I didn't leave myself a ton of room, something that's going to be relatively close to 2, but still gives me room to get closer. So what are we going to do here, guys? Let me do that, and let me do that, and hopefully that's going to be good enough. So the first left-hand interval we're going to come up with is going to be from 1.9 to 2. The second one is going to be a similar interval here, but it's going to get tighter and tighter and tighter closer to that 2 there. So instead of starting at 1.9, we're now going to start at 1.99 and go to 2. And our third interval is going to get even tighter than that. We're going to go 1.999 and end that at 2 as well. So these are what we would consider to be 3 left-hand intervals, everybody. What's happening now is that our x value is getting closer and closer to 2 from the left. And all we're doing then here, everybody, is we are going to find the average rate of change on these 3 intervals. But as each one of these intervals, the first one, the second one, and then the third one, as each of those intervals gets tighter and tighter, you start to see what we were attempting to illustrate right here. That the difference of b minus a, it can never equal 0, but it can get smaller and approach 0. That distance from b to a in interval 1 is 1/10. In interval 2, it's 1/100th, and in interval 3, it's 1/1000th. So we can't ever let our denominator equal 0 or become 0, but we can let it approach 0, and we can see what we can learn from that. Now, this could be a pain in the butt to have to do this 9 different times. So we're going to let the calculator do a lot of the work for us. All right, everybody, so let me go back to where we were. And just to start clean here, everybody, I am going to, let's try that one more time. I'm going to go home, and I'm going to open up a brand new document here and get rid of everything else. So no, I don't need to save my changes, and we'll go fresh here. The first thing we're going to do is we're going to define this function, because it's the same function we're going to use 9 times in a row right here, everybody. So I'm going to go to number 1, which is to add a calculator. And one of the things we're going to do in here the most this year, and I don't know if you did it much last year, is we are going to define our function. Now again, guys, as you're looking at my keypad up here on the left of your screen, pay attention to the red buttons that pop up. That'll show you what I just pressed. To define a function, you could always sit here and manually type in the word that you're trying to do. Now you'll notice I've typed in DEFIN, and that's all italicized right now. But as soon as I hit the E, it stood up straight. That means that the calculator understands what that command means. However, I'd almost rather you guys knew where to find this. Define, we're going to do a lot this year, is under Menu. It's Actions, so I just press number 1, and then number 1 is to define. And we're going to try to define this function here in our calculator. H of x was 1/3 x cubed minus 2x minus 3, so I'm going to call it exactly what it's named. H of x is equal to, and I'll do a 1/3 in parentheses. Oh, forgot my, there we go, 1/3, gotcha. That gets multiplied now by x to the 3rd power. There's an implied multiplication there, guys. You certainly could put times there if you wanted to, but I don't believe that you have to. And then we had what? So 1/3 x cubed minus 2x minus 3. So a minus 2x minus 3, and all you have to do now is hit enter, And you'll notice it rewrote things a little bit for me. It changed my 1/3 into a stacked fraction just to make it look a little bit prettier. So okay, there's h of x. And as I'm hoping you guys have learned from the calculator worksheet, if you were so inclined to know what h of 1.9 was, you can just type this into your calculator the same way you would write it on paper, and boom, your calculator has evaluated that function with an input value of 1.9. That's not really the way I want to handle that, but that is important to know. Okay, where we're going to go next is probably something you guys haven't done before, so stay with me. That reminds me though, you will notice guys right up here, let me move my cursor so you can see it, I am in a document like I showed you to do just a second ago. For those of you who ignored me when I said, hey, do this in a document, and if you're still in Scratchpad, now your luck is running out because what I'm about to do does not exist in Scratchpad. So if you're there, pause the video, go back and watch this again and do it in a document like I said the first time. But for those of us who are here, I'm going to add a page to this document. So much like Mr. Fontana's Google Chrome browser window, you can have multiple tabs up here at the top. I've got about 6 different windows going, each one with about 4 tabs right now. I'm very confused. So guys, to add a page, we're going to hit Control and then the Dock button, which is just underneath Home. If you look above that in blue, it says Plus Page. So we'll do that. And now what we're going to do is we're going to hit number 4. We're going to add a list and spreadsheet to this particular document. All right? So what are we going to do from here? All right, what I'm going to do, guys, is I'm going to label this, no, I'm going to leave that there. I'm going to let the first column here, column A, which I'm in right now, represent the left endpoint of my interval. And I'm going to let column B represent the right endpoint. So the first interval that we typed in started at 1.9. And from here, guys, just like using Excel or Google Sheets, if you hit the Tab button, that moves you over to the right. If I hit Enter, that would have moved me down. And I want to end my first interval right at 2. And I'm going to hit Tab again. Okay, now something interesting is going to happen, everybody. We are now going to type in a function into this particular cell. I do this all the time in Microsoft Excel and in Google Sheets, and people think I'm a frickin' genius. I'd like you guys to be able to learn how to do some of these things too. So, here goes. If you ever want a spreadsheet to do a function for you, you've got to start off by typing in the equal sign. Then from there, we're going to make this do a little bit of work. I'm now going to hit Control and then the division key, and that gets me a stacked fraction. And now what we are going to do is to type in the formula for average rate of change, which was f of b minus f of a all over b minus a. Now, instead of f, we named our function h. So I start off by h. And what we're going to do now is to evaluate h of b, I am not going to type in h of 2, even though my b value is 2 in this problem, because that is only true this one time. What I'm going to do instead is have the spreadsheet look in a location for that number. And the 2, the right endpoint of my interval, was located in cell B1. I don't know if you guys can see what I'm talking about right here, but this 2 is located in column B, and look over to the left, it's in row 1. So I'm going to type in h of B1 minus h of, and my a value, don't worry about what the number is, but think about where it's found. That 1.9 is found in cell A1. Okay? And that's my numerator, h of b1 minus h of a1. Let me hit the down arrow now, and the denominator we had normally written as b minus a. Here it would be 2 minus the 1.9. But again, let's reference the locations. The right endpoint is found, once again, in cell B1, minus the left endpoint, which is found in cell A1. So you're telling the spreadsheet where to look to find those numbers rather than just giving it the numbers yourselves. And if you don't know why yet, you'll see very quickly why it is that we're doing it that way. All right, so let me go ahead and hit Enter now. And because I put equals at the beginning, the calculator actually evaluated the average rate of change of this function, h of x, on this interval from 1.9 to 2. Now we're going to round everything we said to 3 decimal places. So for our purposes, guys, that's going to be a 1.803. So let me go back to my list right over here and write 1.803, and that is the average rate of change of this function on the interval from 1.9 to 2. But we're trying to make these intervals smaller and smaller and smaller so that our instantaneous rate of change becomes more and more like an average rate of change. So now we're going to do all this again, but good news, this is going to become much, much faster now. Let me type in my new A value, which is 1.99, and hit Tab. My right end value, my B, stays at 2, and now for the really fun part. If I go back up into cell C1, there's the formula down there on the bottom. That took a little bit of time to type in, and if I had to do this 8 more times, that would take a lot of time. But the beauty to putting a function into a spreadsheet and telling it where to look is that you can copy and paste this formula, and it will look, now for the next one, instead of cells A1 and B1, it'll now move into the next row and look in A2 and B2. So here's how we do this, everybody. I don't know if you guys know your keyboard shortcuts all that well, but you probably should. On every computer I've ever used my entire life, going back to the late 1980s, the copy command is always Control-C, and the paste command is always Control-V. Now the difference would be that on a computer keyboard, like on your Chromebook right now, you've got to hold both of those buttons down simultaneously. It's a two-hand operation. You hold down Control, then you push C, and then let it go. All right? So, back to this one right here, with your calculator, it's a one-hand operation. You only hit one button at a time. So we are going to touch with one finger, Control, then let it go, and then C. Now, unfortunately, nothing happens on the screen that tells you that you have actually copied that. You just got to trust it. Now I'm going to hit the down arrow, and in cell C2, again, with one finger, one at a time, I'm going to hit Control, let it go, and then V, and it automatically pasted this formula from cell C1 into cell C2. But you'll notice, guys, if you look down at this bottom row, the A1 and the A2 now changed to the A1 and the B1 have now changed into A2 and B2. And that, don't lie, is pretty cool. I can see the smile on your faces right now. So this average rate of change looks like it's 1.98003. I'm glad this came up because I want to talk about this. When we go to round that to 3 decimal places like we always do, a lot of people want to write 1.98 and be done. And their reasoning is there's no point in putting a 0 at the end right there because 1.98 is the same number as 1.980. That, what I just said, is true. However, when the directions say to round to 3 places, you guys might have had this conversation in chemistry when you talked about significant digits. And for us, also at this level, guys, we need that 0 at the end to indicate that we did round this answer to the nearest thousandth and not to the nearest hundredth. So even if that third digit is a 0, you do need to have it there. So you guys can see now, comparing our answer from our interval in number 1 to our interval in number 2, as our interval got significantly smaller, our average rate of change changed a decent amount from 1.803 into 1.980. And let's go ahead and do it one more time. I think you guys are now starting to realize that this really isn't going to be a whole lot more difficult to keep going further. My last A value here is going to be 1.999. Hit Tab. 2, again, for my new B value, which didn't change at all. Let me go back up now. Actually, you know what? I wonder if it's like a computer. I don't even know this. Maybe that formula is still in the clipboard. So if I just hit Control-V, hey, look at that. I learned something new. I didn't know that. You don't have to copy it a second time. So rounded to 3 decimal places, we are now 1.998. Everybody. So 1.998 is our new average rate of change. Now, if I were to stop right there If the problem just said, estimate the instantaneous rate of change at x equals 2, I'm now going to take a look at these three numbers right here. And what I'm realizing now is that as my interval, b minus a, gets smaller and smaller and smaller and approaches 0, it never equals 0, but it approaches 0, look at your three average rates of change. They are beginning to approach one finite value, and I think we can see, guys, the value we are approaching here is 2. So the left-hand intervals certainly seem to suggest to me here that the instantaneous rate of change of this function at x equals 2 is 2. That would be my estimate right now. Now I'm going to go ahead and knock out the rest of this much faster because I think we get it. The right-hand intervals, again, I'm going to do 3, everybody, but the difference now is these are all going to begin at 2. So we'll go 2, and again, I'll do 1/10 for starters, 2.1. We will do from 2, and now we'll go 1/100th, 2.01. All right, and lastly here, we're going from 2 to 2.001. We'll go with 1,000th for that last one. So now that I think I get it, I think this is going to go pretty darn fast. All right, I'm going to go back over into the A column. Hello, computer. There we go. And I'm going to go ahead and type in 2, enter, 2, enter, 2, enter. There's my 3 2s. And now my right endpoints, my B values, are going to be 2.1, 2.01, enter, 2.001, enter. And now let me show you another little cool trick. You can paste the same formula into multiple cells at once. All right, so what I'm going to do, and again, this is similar to the way that a computer works. I'm on cell C4, but I'm going to hold down the Shift button here, everybody, right above the 7, and then hit the down arrow twice. Now, if you saw what I actually just did, my smartboard emulator works different than yours. You guys, this is a two-hand operation. Hold down Shift and hit down as many times as you need to. For me, I got to go Shift, down, and it's kind of a pain. But now that we've got multiple cells highlighted, now we should be able to type in Control V yet again. And now, like that, lickety-split, we came up with 3 new average rates of change. 2.203 is the first one. 2.203 is what I said, sorry. We've got 2.020. All right, and the last one, which of course is probably the most accurate, 2.002. So let's read this again, everybody. Our intervals are getting smaller and smaller and smaller. So once again, the quantity b minus a is approaching 0. And let's take a look at our average rates of change. We started here with that one, but of course, the tighter the interval, the more accurate we are. And we can start to see, everybody, that as b minus a on the left is approaching 0, our average rate of change on the right seems to be approaching 2 yet again. So that really shouldn't surprise us. We ended up with the same estimate here for the instantaneous rate of change, regardless of which way that we did it or which way we approached it. And I want to go ahead and show you the last one real quick. The one that I like the most. Your author really seems to push those two ideas there, the left-hand intervals and the right-hand intervals, but I'm really a big fan of symmetric intervals. Let me show you what I mean by that. Instead of using the actual point in question of 2 as one of your endpoints, I'm going to start off by going 1/10 of a unit to the left of 2 and 1/10 of a unit to the right of 2. It's symmetric because both A and B are the same distance away from 2. Now I'll do the exact same thing again, but we'll talk about hundredths instead of tenths. So I'm going to go 1.99, which is 1/100th to the left of 2, to 2.01, 1/100th to the right. And we'll do the same thing now with thousandths. 1.999, 2.001. The midpoint of each one of these three intervals is 2. And something cool is going to happen there too that I want you guys to see. So let me go down now to cell A7, and we said we were doing 1.9, and then below that 1.99, and below that 1.999. And if I go back to cell B7, my B value there was 2.1, enter, 2.01, enter, 2.001, enter. And I believe I still have the same formula in my calculator's clipboard. So again, I'm going to hit Shift. You guys would hold down Shift and hit down, down now, but I've got to go back and forth like this. So we will highlight cells C7 through C9 and then hit Control V. And what you notice this time, everybody, if we round to the nearest thousandth, we start off with a 2.003, but then after that, both of these are going to round to 2.000. Notice though, guys, you can see more digits right here than just 3. This one right here isn't exactly 2.000, and actually I don't think this one is either, but when we round to the nearest thousandth, they're going to look the same. So let's write this out, everybody. This was 2.003, but this was 2.000, and this was 2.000. But hey, let's read it again. As our intervals get smaller and smaller and approach 0, our average rates of change go from here to here to here. They certainly seem to be converging on the value of 2. So everybody, that was way more time spent on that problem than we absolutely needed to do, but I wanted you all to see that there are 3 different ways of doing this problem, but all of them will get you the exact same answer of 2. It just requires you guys to kind of look at this thing a little differently and to try to test for convergence in each one of those cases. So, all right, I thought that one was fun. All right, we're going to move on in just a second right here into some free fall constants. I'm going to pause this video for just a quick second, everybody. Okay, so let's keep going now. What we're going to start to get into next is another series of problems here where we're going to use the calculator to do a lot of the grunt work for us. But before we go any further, it's probably a good time to just take a little time out and talk about a few things that are going to be important to us moving forward. Those of you who have taken physics already probably know where we're going with these things already. Those of you who haven't, this might be news to you. But this is information that we need to have in order to start doing free fall problems, which we do quite a bit of throughout the course of the year. So when we talk about free fall constants, it's first worthwhile to note these are only true on Earth, everybody, which, I don't know about you, is where I tend to spend the majority of my time. But if we did do a problem on the Moon or on Mars or some fictitious planet out there with a different gravitational pull, all of this would be out the window, where it would fall at a rate different than it would fall on Earth, but I digress. All right, everybody, a of t, the acceleration function due to gravity on Earth, everybody, a couple of different ways of looking at it here is, depending on if you do this here, guys, with metric or with empirical units right here, -32 feet per second squared. All right, using US units or British units right there, that's what it is in that regard. And using the metric system, that is going to be a -9.8 meters per second squared. Notice both of those are negative, and that's not a mistake. That is because gravity has a tendency to pull things downward. And we talked about how anything moving down is losing position, which means it's going to have a negative velocity, which means it's going to have a negative acceleration as well. So those are 2 numbers to know here, and you should know what units they are, guys. We need to have those memorized, is what I would normally tell you for our first quiz or test. This year it's a little bit different. And then last one, the formula here for displacement, or the distance that an object falls during t seconds of free fall, you might be able to figure out where this is coming. This is a -16 t squared, and when we're talking about a distance here, everybody, that 16 t squared is going to be measured in feet. So what that means is if you want to know how far an object falls during, let's say, 3 seconds of free fall, you'd go ahead and put a 3 in here for t, square it to get 9, and multiply it by -16. That means that an object moves -144 feet during free fall, or its displacement is -144, meaning that it's falling down that far. In the metric system over here, that is going to be a -4.9 t squared, but now we're measuring things in meters. So those 4 quantities right there, everybody, are, ooh, that was ugly, are pretty important to know, and we want to make sure that we've got those down, that we understand what they are, and more to the point, how to use them. So maybe put a big box around this. Maybe we should have written that at the very top of our notes, but let's use it. We're going to do one big stem here, everybody, and do a whole bunch of problems based on this one thing. Okay, so what's going on in problem number 5? An object is dropped from the top of a 500-foot tower, and we've got a few things that we've got to work on. Now, to try to clarify some things, I'm going to try to draw a really pretty picture of what's happening. That, ladies and gentlemen, is the ground. And then I'm going to draw a tall tower that is 500 feet up in the air. So right up here, that's going to be 500 feet. I don't know if you guys knew this, but Mr. Fontana was almost an art teacher before becoming a math teacher. So anyway. All right, so where are we now? Object is dropped from the top of a 500-foot tower. That's really all we have so far. What's going on in A? Write a function that gives the object's height, h, above the ground, t seconds after it is dropped. Okay, so back to our brilliant diagram here. So we've got somebody who's standing right up here. That was supposed to be somebody who was a different color. There you go. So we've got somebody right up here, and they're holding something out, and they're dropping an object, and it is going downward, as things tend to do because of gravity. And we're going to try to come up with a function right now that tells us what the height of that object is as a function of t seconds after we let that object go. So if we think about this logically and chronologically, I would ask you this question. At the moment you released the object, it began with what height? And the answer to that, 500 feet. So we're going to start with that. We begin with a 500 there for the constant in the beginning of this function. But then, as time goes on, this object is going to lose height. And the amount of height that it loses is what we came up with right here, you guys. Delta S, the distance that an object falls during t seconds of free fall. Now, you'll notice that I already made the choice right here that we were going to be using feet and empirical measurements right here. So we're going to go with this version of displacement, a -16t squared. So 500 feet minus 16t squared, that's going to get you the height of this object t seconds after free fall. So I wrote the answer here, but it probably would have been better to put here, that h of t. Oh, and by the way, I told you guys to name this function h, but it would have been perfectly fine if you guys had called it s of t, because s means position and height means vertical position specifically. Both of those would have been fine here. But you start with 500, and then there's a -16t squared. The only other thing that will sometimes complicate this function, although not in this problem, is if you, at the top of that tower, were to impart an initial velocity onto that object by throwing it up in the air or by throwing it down. If you had tossed that thing up in the air, let's say with an initial velocity of 50 feet per second, you actually would have added a 50t right here. And now you end up with a full quadratic trinomial. But this problem said nothing at all about throwing the object up or down. In fact, the important word here is dropped. And when something is dropped, that means that it is simply released, and we didn't put any effort into throwing this thing up or down. So I'm going to get rid of that, and there's our answer to part A, and here's our picture for it. So that is our h of t function. The only thing I know so far, everybody, is that at the moment that we drop this object, its height was 500. So that means that when we put in h of 0, let's think about that, it's 500 minus 16 times 0 squared, we end up with 500 feet. That makes total sense to me, everybody, because as we look at this diagram here, it would appear that the object has a height of 500 at the moment that we let it go. So I'm going to go ahead and put a little point right here, I guess. And that ordered pair then is going to be our time value, which is 0, and our height value, which is 500. Sometimes people get confused as to whether to make that 0 500 or 500 0, and really it could work either way. But remember, guys, that the reason we normally put x first and then y is that x is usually called our independent variable. X can be whatever it wants to be, and the value of x does not depend on, it is not determined by the value of y. Usually it's the other way around. Y is the dependent variable, and to figure out the value of y, you take the value of x and do whatever you need to do to that. Well, in this case, it's the time value that determines the height value. Okay, let's move on to part B. Important question here, how long does it take the object to hit the ground? Well, back to this diagram, we certainly know, although I don't think I drew this very well, why is my ground didn't move when I moved the diagram. That's important. Okay, so what's going on right here, guys? Well, there's one thing that we do know at this spot. We do know that when this object hits the ground, its height is now 0. But what we don't know yet is how long it took to get there. So this ordered pair is going to be something, comma, and a height of 0. So with that in mind, let's go back to this height function that we just wrote and let's see if we can't make it work for us. The only thing we know about this object right now is that its height is given by the function 500 minus 16t squared. Well, at this particular moment right here, guys, we are looking for a value of time, but we know that the value of h, our height, is 0. So back to this formula, if I'm looking for a value of t, that's what I'm trying to solve for, but we better know what to put here. And we do know that at this moment in time, the height of our object, when it hits the ground, is 0. So we'll set that equal to this expression of 500 minus 16t squared, and we will use this thing called algebra to solve this equation for t. We'll bring the 16t squared to the other side to make it positive. Nice. We will divide both sides by 16, and I know that I can simplify 500 over 16, but I really don't care right now. You'll see why in a moment. And then I know that to figure out t, I've got to take the square root of both the left and the right. Now, one thing we've talked about already that I'm hoping you guys know is that anytime you take a square root that wasn't there before, there should be a plus or minus in front of it. But let's think realistically here, everybody. We are solving for t. We're trying to figure out how much time it takes this object to fall that far, and there is no way that time can be negative. Our domain here for t would be from 0 to infinity. So we can forget about the plus or minus when we're solving for something like time. And we are going to get t equals, and I got to show you guys something here interesting about your calculators. I don't want to be here right now, so I'm going to go back to my calculator page. The way I'm going to do that, everybody, is hit Control and then the left arrow on the D-pad. And that takes me back over to the 1.1 tab, which was my calculator page. So we are going to take the square root of, and I believe we had 500 divided by 16. Now when you hit enter there, your calculator is going to do a nice thing for you. It's going to simplify a radical. That becomes 5 root 5 over 2, and I'm certainly going to trust it. But I'll tell you guys that most of the world out there, even in this year here, as far as we are away from the TI-84, most of the world is still using the 84, and they're going to want this answer as a decimal. So for us, everybody, I'm going to hit Control Enter. Now you want to look right here. Oh, whoa, 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 whoa. Let's try that again, Mr. Fontana. You want to look right, where am I? I don't want to go there. Okay, you want to look right here and make sure that this expression is exactly the same as this expression was above it. For a reason that at least one of you learned the hard way already on your quiz, this is a spot where your calculator sometimes gets wonky on you. But yeah, that's exactly what I wanted, and so my answer as a decimal, 5.590, is what I'm going to write down on my paper here. So t equals 5.590. Now, ladies and gentlemen, we are going to use that time value a little bit later on. So we're going to go ahead and name this something important. I'm going to call that A. In fact, an arrow was a stupid idea. Let me go ahead and put an equal sign. Now I'm going to use my calculator and store that value. So we just got this answer of 5.590, and this was also on your Inspire CAS worksheet. I'm going to hit Control, then this variable button above the 9, and you'll see the second function of that is to store it, and we're going to store that value into A, and there it is. Now if I ever need that number again, without having to round it, I can just type in A, and boom, there it is stored quickly for us. Back in the late 80s, your calculators could store one number for you at a time. Now, your calculator will store, I think you guys are thinking 26 right now because there's 26 letters in the alphabet. It's actually way more than that. You can combine things so that AB is kind of like its own variable, or QR, something like that. So, and it's more than that too. I don't know that there's a limit to how many, I'm sure there is, to how many you can store there. But let's keep that in mind. Okay, so back to where we are right now. How long does it take the object to reach the ground? I think we've answered that. I would like to include some units right there. This is definitely seconds, because that formula we used of 16t squared only is relevant when t is measured in seconds. So that's how long it takes this object to fall. Okay, on to C. What is the object's average velocity during the entire fall? All right, well, this is what we've been talking about for a while. The formula for average velocity is going to be f of b minus f of a all over b minus a. Or, since we named our function h, we're going to go with h. And let's think about what our b value is. We're talking about here during the entire fall. And as I think we just established in the last problem, the entire fall, everybody, is a time interval starting at 0 and ending at whatever that a value was. I think it was 5.590 if I'm not mistaken. But the great thing about storing it is I don't have to remember it. All right, so I can go ahead and just write on my paper h of a. Guys, I can do that, and I'll allow you to do that on a quiz or a test, because somewhere on my paper I wrote down what a was. And now when Mr. Fontana goes to grade this, if he's confused about what it was that I meant when I said a, all he has to do is look somewhere on the paper, and if he sees that a is equal to 5.590, well, that's a faster way for me to get that expressed. Okay, good. So it's h of a minus h of the beginning time, which is 0. And now for change in x, a minus 0 goes down there on the bottom. Okay, so that wasn't that bad. So we're going to go ahead and figure this out. Although I'm going to show you guys another little trick right now that's going to take some time up front, but it's eventually going to make your life easier. Finding average velocity isn't really all that bad, and I do know that I'm going to do this multiple times now moving forward, we're going to go ahead and try to make it a little bit faster. We're going to define ourselves a new function here for this one particular problem. Actually, two. Let me show you what's coming next, guys. Menu 1.1. We're going to define the h of t function that we've already found here for this problem. We started with a height of 500 feet, and we lose 16t squared feet for every second that this thing is in free fall. I hit enter, it tells me done, and there are no problems. The next thing we're going to do, and you guys should do this with me right now, and then keep using the same document for the rest of this chapter. No, I'm not kidding. We're now going to define a new function here that does the average value calculation for us. So I'm going to call this formula AV. That's the name I'm going to give it for average velocity. Now, the average velocity function, you've already written this down in your notes, requires not one, but two inputs. So, I just realized a little problem with what I did here. I don't want to use A and B because we've already come up with a value for A. Maybe I should have named that something different. Well, now I know. Okay, so let's call that something different. Why don't we call it average velocity on the interval from y to z? You guys can use any variables you want. And we're going to define that function as being a difference quotient. And in the numerator, we are going to take the h function, and we're going to evaluate it at the right endpoint of our interval, which we just defined to be z. So we're going to do h of z minus the first y value, or h value. That's going to be h of y. And on the bottom, we're simply going to do the same thing, but just the x values now, z minus y underneath. So I hope I'm not confusing you guys by using h's instead of f's and y's and z's instead of a's and b's, but in a way I don't care. In a way I want you to be just a little bit confused for a moment, and then I want you to look at this and realize, oh, it's really no different than anything that we've done before. We're just putting in whatever variable we want for this particular problem. So we hit enter and it says that we're done. And now the cool thing is, if I want to find, like we're doing right here, the average velocity of our h of x function, starting at, where am I guys? Starting right here at 0 and ending at a having been stored in the calculator, watch how easy this is. AV starting at 0, comma, and ending at a. And when we hit enter, boom, guys, there's the answer of negative 89.443. So I don't know how much you guys have done of this in the past. Anybody who's taken computer science in the past knows a little bit about what I'm talking about. But if you're confused as to where this answer right here came from, it all comes from this and this. The AV function uses the variables y and z, and it uses the h function that we defined up here on the line above. Okay, so the calculator just did a ton of work for us, and now that we took the time to put in those values early on, the rest of this is going to go really, really fast and easy. So the average velocity from 0 to a was that 5.590 value, is negative 89.443. So let me write that out. Negative 89.443. The units, lest we forget, let's go back to this line right here. Average velocity was change in position over change in time. H was being measured in feet, and the time was being measured in seconds. And feet divided by seconds are simply going to get us feet per second. So that's our average velocity, everybody, during the entire free fall. So coming all the way down here in red, I'm going to write this over here, the average velocity was negative 89 I forgot it already, 443 feet per second. And of course it's negative because we're moving downward. Okay? All right. Good times, everybody. So that took us through B. Now for C, I'm going to ask you some similar questions, but slightly different. What's the object's average velocity during the first 250 feet of free fall? So back to my beautiful diagram, I'm going to switch to green now, everybody. And now instead of being worried about the whole thing, we only want to know what happens during the first 250 feet of free fall. So as the object goes from where? From that same height to right down here, we're going to do the same work that we just did. Okay? The only difference is that we now need to figure out a couple of things. This was 5.590 seconds, which of course we defined as A. We've got to figure out what's going on right here, you guys. I'm going to keep doing that in green, okay? We do not know the time value yet, but we do know that at that moment, the object has fallen 250 feet from a height of 500 feet, so its height is 250. And we've got to figure out this t value here, kind of in the same way that we figured out this t value earlier. So back to it, guys. We are once again going to use that initial function that h of t was equal to 500 minus 16t squared. And we now want to know what time value is going to give us a height of 250. So that will be set equal to 500 minus 16t squared. Oh, let's see, and I'll bring the 16t squared left, I'll bring the 250 right. So 16t squared equals 250. So t then is going to be the square root of 250 divided by 16. Now before we type that into our calculator, I want to ask you guys to think about something here. Let's just say, for the sake of simplicity, it took 5.6 seconds for this thing to fall. My question for you guys is, if that was 5.6 seconds, then right here, when we have fallen half of the distance, do you guys think that this is going to be half of the time? Half of 5.6 would be 2.8 seconds. Hit pause for a second and think about that. Okay, you're back. All right, it would be exactly 2.8 seconds, half the time on the way down, if this object fell with a constant speed. Then things would be linear and you would cover half the distance in half of the time. That's kind of true if you're just walking in a straight line over even terrain. But because this object is being acted upon by gravity, it is accelerating, it is speeding up on the way down. That means that this first leg of the journey from here to here is where the object is traveling more slowly. And the second leg of this journey right down here is where the object is traveling faster. And if it's traveling more slowly up here at the top, is it going to take more or less than half the time to cover half the distance? Well, if it's traveling slowly, it should take more than half of that time. So I'm expecting a value here greater than 2.8 seconds. Let's keep that in mind and let's see if we are right. Okay, so back to this right here, we need to go to the calculator now and take the square root of 250 over 16. Okay, again, if I just hit enter, it's going to give me a radical version. I don't want that, so I'm just going to immediately hit control enter, and it did take more than 2.8 seconds. In fact, it took a lot more than that, 3.953 seconds to go half the distance. Let's do that here. Okay, so t was equal to 3.953 seconds. And as you guys may have guessed, I'm going to store that value and I'm going to call that B in my calculator. You'll see me do that in just a second. So back to it, 3.953 seconds, and that's the value that we're going to store as B. So how do I do that? Back to my calculator, I hit Control, the variable button, and now I just type in B, and there we go. Now, the reason I did that is because, and I'm sorry, I wasn't done with this problem right here. Nope, wait, yeah, no, this one. The question was, what is the object's average velocity? So we now need to do an average velocity, but I'm going to go ahead and write this out now the way I will in the calculator, starting at a time value of 0 seconds and ending at a time value of B. And again, I can say B, I don't like where I put this, guys. I can say B because I've defined in my calculator already, or excuse me, on my paper already, what B is. So now it's calculator time again, and once more I'm going to hit AV for average velocity on an interval starting at 0 and ending at B. And survey says negative 63.246. Negative 63.246. And once again, the units are going to be feet per second. So that is the answer to what we were looking for right here. And if we go back to the beautiful diagram, negative 63.246, oh boy, we got a lot going on. I'm going to get rid of this and now say in green that our average velocity was negative 63.246 feet per second. Let's compare that value to this value right over here. We said a while ago that the top half of this should be the slow half. And in fact, guys, you got to be careful right here. the velocity here is actually greater than the velocity here, but speed is not. If we didn't catch this in physics at any point, speed is the absolute value of velocity. So all of these velocities are negative because the object is going downward. But when you're thinking about whether it's traveling faster or slower, ignore the negatives. The 63 here is slower than the 89. So it's slower during the top half than it is during the entire travel. Okay, let me get rid of this, and I think we're in pretty good shape. What's coming next? I bet you could guess. What is the object's average velocity during the last 250 feet of free fall? So the last 250 feet, I think I'm going to do this in green again, everybody, would be this stretch right over here. And lucky for us, we know the time value we're starting at, that's B, and we know the time value that we're ending at, and that's A. So we don't have to find a time value here. We already know the starting and the ending values for this one. So we're just doing the average velocity starting, this is a little backwards what you might think, starting at a time value that we saved as B and ending at a time value that we saved as A. Now before we type that in, ask yourself this question again. Do I think that this answer right down here for average velocity on the bottom, do I think that it should be slower than 63, okay, or between 63 and 89, or should it be faster than 89? Hopefully you guys have an answer to that. This is the last leg. This is when it's traveling the fastest. So I got to be careful about how I say this. The speed of this object should be greater than either speed we have found before. It should be greater than 89.443. But be careful, because of all of our velocities being negative, the velocity actually should be less than negative 89.443. So let's punch it in, everybody, and see what we get. Average velocity starting at B and ending at A. Survey says negative 152.688. Negative 152.688, and that's going to be feet per second as well. And guys, that did what we thought it should do. This is where it's traveling the fastest. So negative 152.688, and once again, feet per second. All right, so as you can see, these problems are starting to take less time as we're starting to get the hang of them. I think I'm going to skip this problem with you right now, guys. This would require us to find two new time values for the middle 250 feet, and I got to wrap this one up here pretty quickly, and I know you guys are bored there. So let's talk about this one real quick, and then I think we're done with this section, guys. Use a table to approximate instantaneous velocity when the height of this object here, guys, is at 250 feet exactly. So we've already answered this. At 250 feet, that happens now, guys, at a t value that was equal to b, if I'm not mistaken. Let me go back and double check that. A height of 250 feet happened right here, yep, at a t value of 3.953. So let me write this out here, 3.953 seconds. And there's three different ways we could do this problem, you guys. I like the symmetric difference quotient the best, so I'm going to run with it that route. What I'm going to do first, you guys, without thinking very hard, is I'm going to try to come up with one interval of time that encompasses 3.953. And the way that I like to do it best is to start with 1/10, then go to 1/100th, and then go to 1/1000th. So 1/10 of a second less than this would be 3.853. 1/10 of a second more than that would be 4.053. In a moment, we're going to find the average velocity on that interval. Then we're going to do hundredths. We're going to go 1/100th less than b, so that'll be 3.943 to 1/100th more than b, which is 3.963. We'll find the average velocity there. But of course, as I think you guys know what I really want to do, thousandths are even better. So I'm going to go just 1,000th less, 3.952 to 1/1000th more than b, 3.954. And you can kind of see that the midpoint of all of these intervals here ends up being this actual b value that we're looking at. Okay, so with that in mind, this is kind of a pain, but we're going to go ahead. And like I said, guys, because I'm a little short on time, I'm going to trust that you guys could come up with these answers on your own, but I'm just going to go ahead and find the one that really matters here. The smallest interval is going to give us the best estimate for instantaneous rate of change, or in this case, instantaneous velocity. So everything is still the same now, and we're going to do average velocity starting at 3.95, shoot, was it 2 or 3? 952, comma, and ending at 3.954. Let me make sure I type that in right. 952, 954, there we go. And our answer here, everybody, is going to come out to be negative 126.496. Negative 126.496, and the units once again are going to be feet per second. Now when it's said to use a table, everybody, this is kind of the table that I've created right here. I just didn't really draw it out as such, which was maybe dumb. Maybe instead of those arrows I should have put this, and you guys would need to come up with values here and here to get full credit. Let me say one more thing before I shut up and turn this off. Everything that we've done in the calculator now is unique to this particular problem, with the exception of the actual AV function. So what you guys should not do right now is you should not be making a new document, because if you do make a new document, all of these existing functions are going to go away. And now what's going to happen here, guys, is that this average velocity function, that's a formula. So this one always works. But this is where you have to be careful. This h of t function right here, which this function references, this function was unique to this problem. So when you go to start your homework and it now asks you to come up with an average velocity, all you guys need to do is redefine h of t. Not this function. Leave that one alone. But every new problem that you do, you're going to have to redefine h of t with a new starting position, maybe a different acceleration if you're talking units. And by the way, the way you redefine a function, let me just hit Control, oh no, wait, what do I want to do right here? If I just hit Escape, there you go, that takes you down to the bottom. Okay, why did that happen there? Enter, all right. If you were to just write over it, menu 1, and if you were to define h of t, you'll notice that the h came up bold because it's already defined, right? But if I were to define h of t as something new, maybe now my initial height was 57 feet, and maybe now I'm doing metric, so it's minus 4.9 t squared, okay? So there's your new h of t function. Watch this, guys. If I go back and I do the exact same computation that I did 2 lines ago, I got a different answer this time. And the reason why is because now this AV function right here is referencing this h of t function, not the original h of t function that was being referenced right here. So computers are only concerned about the most recent name for a function. So every time you do a new problem, you guys should be redefining h of t. Whew, that was a lot. Long section there, guys. Good luck with everything. And when you have questions, post them in comments and let me know. Good luck, everybody.